the next presentation here is designing a CAN to time sensitive network Ethernet gateway, and this will be by Dr. Nikos Zervas, and he is CEO of Cost Incorporated, where he served as a vice president of marketing and engineering, and he has co-founded and the CEO of Alma Technology, and bootstrapped it to become a reputable IP provider for image and video compression and cores. And Nikos has a BA and a PhD in electric and computer engineering, and his research has been published in over 40 technical journals, conference papers, and has been honored by IEEE. So please, Nikos, take the screen.
Thank you very much. So today I'm gonna talk about a design of a CAN-to-TSN Ethernet gateway. And even though we are in a CAN conference, I'm gonna start by outlining the benefits of TSN. TSN is a group of standards that cover all different aspects of network functionality, from time synchronization to traffic shaping and so on, which combined together, they're able to deliver highly available, highly reliable communication with ultra low latency and to a large extent deterministic latency over Ethernet, which is very well aligned with what automotive networks require today. So because of this great work that the IEEE committee is doing, a lot of people believe that TSN Ethernet will replace CAN eventually, but there's some counter argument on that. And I'm one of those who believe that this is not going to happen anytime soon. And that's because even though TSN Ethernet offers higher bit rates and therefore lowers the integration cost for high bandwidth sensors that we need more and more, like LIDARs and cameras and so on, there are aspects of CAN that they make CAN bus highly attractive, and that's not going to change in the future. So regardless of whether it is 5 or 8 megabits per second or 4 or 2, this is not that slow for many types of applications within a car. The CAN also uses the available bandwidth in a much more efficient way than TSN does or Ethernet does when you have short messages, because of the lower overhead with in terms of headers and so on, and can have much better latency and jitter. But even more importantly, it is simpler, it is proven, it is reliable. We have a large number of already certified ECUs and devices, and it is widely deployed. So that means that the in-vehicle network will not change, at least on an abstract view, very rapidly. Today, we have networks that look like what we have here on our slide. The network is divided in domains. In each domain, you typically use one protocol. Here we have the red identifying CAN and the blue identifying TSN. So for each domain, you would have a domain control unit to perform the control functions, and then the different domains would be connected to each other via an Ethernet backplane and to a centralized control unit. So what will change in the future is that we would want to transfer some of the intelligence currently assigned to a domain control unit to the central control unit. We would want to get information from different domains, fuse that data, make more intelligent decisions, and then feed back in real time to back to the domain. But in order to do something like that, you need fast communication between the domain and the control unit. And what stands in the way of that is these gateways that translate from one protocol to the other. So these gateways already exist in automotive networks, but they're not standardized, and that makes the testing and development quite expensive, and it also generates interoperability issues. More importantly, or equally importantly, they are typically implemented with microcontroller units, which means that the gateway functionality is implemented in software, and software can be slow, limiting bandwidth and increasing latency. So as we move forward, we would need more standardization on the protocol layer and so on. But we would also need custom hardware, and custom hardware would enable us to go at really low latencies, or the latency levels that are required for real-time control when crossing those gateways. So we have tried to develop a gateway like that. It's a custom, and we developed a custom hardware data path, but using commercially available IP cores. So we use a CAN controller IP core, a UDP IP hardware stack, and a TSN endpoint, simple or sweet. And in both cases, in both directions, from CAN to Ethernet and Ethernet to CAN, we were able to get latencies that were below 30 microseconds, which is sufficient for many control applications. And then the design had 7 CAN ports, each separately configured with its own parameters. And on the Ethernet port, we could do 101 gigabits per second, and the whole thing is configurable over the Ethernet. So that's the abstract view of the gateway. But in the process of designing that, we had to answer a number of questions, like, do we do Ethernet over CAN or CAN over Ethernet? Which protocols exactly should we use on the Ethernet side? Do we do tunneling or protocol translation? How do we deal with network bandwidth utilization? What kind of topologies can we serve? And more importantly, does latency through the gateway allows for real-time control, or just monitoring, configuration, and diagnostics? So I'll try to go quickly through the decision-making process and the thought process we followed on some of those questions. I'll start by saying that we decided to do CAN over Ethernet and not Ethernet over CAN, and that was a relatively easy decision. If you just take a look at the frame formats, you would see that the Ethernet frame payload is 46 to 1500 bytes. But then on top of that, you have another 26 to 30 bytes of headers on just the Ethernet frame. And then if you use IP, that adds another 20 bytes of headers, and UDP would add 4. And if you're using TCP, then you get 20. And compare that to a CAN or a CAN-FD message, you only have 8 or 64 bytes with CAN-FD. If you wanted to include the information included in an Ethernet frame, you wouldn't have enough space to even keep the headers in there. So that means that if you wanted to do CAN over Ethernet, Ethernet over CAN, you would have to break each Ethernet frame into multiple CAN messages, and that would complicate things and make things messier. So we went let's say the obvious way, if you may, and went for a CAN to Ethernet setup. Then the easier thing to do is to implement tunneling. So embed entire CAN messages within Ethernet frames, but we had to decide exactly at what layer we wanted to do that. Do we do that at the Ethernet level, at the IP frame level, at the TCP or UDP? So the thought process here is, again, relatively simple. We had to use IP because IP is the basic switching method for almost all automotive networks. So we had to go up to that layer, and then TCP did not look like a great option because yes, it is TCP offers reliable communication, but that's on the presence of a non-reliable network. In the case of a reliable network where you don't have packet loss and so on, the handshaking from TCP/IP just introduces unnecessary traffic in the bus or in the network and excessive latency. So UDP seems like a better choice because UDP, which is best effort and not reliable in the general case, becomes reliable when networks you don't lose information over your networks because of congestion like TSN does, and you don't have connection losses or liners, which are unacceptable in most cases in the automotive networks anyway. So we decided to go tunneling. We decided to implement tunneling of CAN frames over UDP. That would also simplify the application level development since software for managing UDP and messages is very widely used. So so we stepped back and said, okay, we're gonna embed CAN messages within UDP frames, but then that means that if we had an 8-byte frame or 1-byte frame, we would consume 50 header bytes for the Ethernet frame, the IP frame, and the UDP frame, and that's a lot. That's a lot for a single CAN message, which in the best case can be the payload, the useful payload can be 64 bytes. So we figured that maybe if we grouped messages together, that would improve the whole bandwidth utilization, because now the overhead of headers would be distributed over the different messages. But then waiting for more frames to arrive would actually destroy our latency characteristics. So what we end up doing is we developed this method, applied this method where for each CAN port of our gateway, we wait until we get X number of frames, where X is a user-defined parameter. It is a runtime programmable parameter. And we stop waiting if Y nanoseconds go by. So this way we can actually trade latency for better bandwidth utilization where we have. So if we have a high priority CAN port, we would wait some more bandwidth, but for those ports that are used, for example, for diagnostics and what have you, we will have a better bandwidth utilization this way. The next thing we had to deal with was the addressing and the priority. So we have here to build a bridge between two protocols that are different in their very essence. CAN is a bus, and it uses a single field, an 11-bit or 29-bit CAN ID, and that ID encodes the data type, the priority, the source, the destination, anything there is to any information related to the payload itself. It is encoded with this CAN ID. And on the other hand, you have Ethernet, which is a point-to-point connection, and it's not a bus. So Ethernet relies on source and destination addresses. So you have the MAC address on the Ethernet frames, the IP address, and the UDP ports on the UDP frames. And then you only have 3 bits for priorities. These are the 3 bits of the VLAN tags, which is what TSN also uses to identify the traffic class. So we were trying to figure out how to bridge those 2 words. And we had to do that because if we wanted to do any real-time, if you wanted to take into account the priority at least of frames in real time, we couldn't rely on software processing the actual frames in order to do that. So we ended up doing the following. We associated its CAN port with a UDP port and a VLAN tag for a TSN traffic class. And then its port is also configured independently to accept different CAN IDs. So by doing that, we actually can directly link a group of CAN IDs to a specific UDP port and traffic class. So when on the direction from CAN to Ethernet, on a specific port, we collect a specific set of CAN IDs using the filters on the CAN controller, and that gets forwarded to the IP address, UDP port, and as having a traffic class. And out of that, the traffic class is statically associated with a port, and so is the source port. The rest of that is runtime programmable, and the application can change it to anything. And on the other direction, we get something on the gateway IP address, and then the UDP port would actually get us to the right port. So it is a UDP port that is associated with a specific physical CAN port. And by doing that, we are able to serve different use cases. The first one is one where we have the different ports of the gateway connected to the same CAN bus. Something like that would be, you would want to do something like that so that you get different priorities or different groups of CAN IDs with different latency on your TSN network. Again, you can use grouping to better utilize the Ethernet bandwidth on the lower priority traffic, and at the same time have ports associated with a high priority traffic that gets directly to the Ethernet side. So with a setup like that, you can have you can serve the purposes of configuration, monitoring, but also real-time control of a single CAN bus. Then there is the use case where the gateway can be used to for integrating CAN devices directly in a TSN network. So these are the cases where you've designed your domain to use TSN Ethernet, but then you have these sensor or actuator that you can get access easily to, but that has a CAN connection. So you would want to integrate that easily to your domain, and that's the setup here. So there you have one port associated with one CAN ECU, not a CAN bus. It's a point-to-point directly. And that allows you to have control over that CAN node over TSN. It can also serve the purpose of bridging CANs over TSN. That's easier to visualize in the next example use case, where we have a mixture of use case A and use case B. So in this case, we dedicate a number of ports into one bus, another number of ports into a different bus, and then a fourth port here to third port here to a dedicated device. So here we could actually go bridge CAN bus on the left side to CAN bus on the right side via TSN. And we could even implement control functions that cross that boundary over here, the local bus boundary. So with this setup, you can have a mixture of the benefits of the other, and therefore you can use it for centralized configuration, monitoring, and control. And you can do that with, I mean, if you would assign just one bus, one port to each bus, then you could have up to 7 buses connected to the same gateway. And on the Ethernet side, you can obviously do anything. If you would use the gateway with the simple TSN endpoint, you would have to go on a star topology where you connect your gateways to a switch, and from there to the rest of your backbone or your network anyway. But the same gateway can be configured to be a switched endpoint on the TSN side, and that would enable you to daisy chain on the Ethernet side, or use the redundant connection for improved reliability. So these setups are also possible with a proposed gateway. So if we wanted to summarize what I presented today is a low latency multi-port CAN-to-TSN gateway. That gateway was designed with custom hardware, but based on commercially available IP cores. And what we got out of that is a design with less than 30 microseconds latency on either direction. Now, by saying less, it is close to 30 microseconds though, right? So if you want to go significantly lower than these 30 microseconds, one would have to develop a dedicated cut-through architecture rather than the approach of the assembly of IP cores that we've used. Most of these IP cores that we use, they have buffers in them for CAN frames or for UDP frames or your IP frames. So it's more like the assembly is more like a store and forward architecture rather than a cut. So if we wanted to go for even lower latency through the gateway, we would require a dedicated cut-through architecture. And on the other hand, if higher latency is tolerable, then part of the functionality that we currently implement on custom hardware could migrate to software. But I think this is the direction where you would end up with a gateway that would be useful for monitoring, maybe configuration, but not for real-time control. Then we used a method for that maps the CAN port and CAN ID group to a UDP port and a traffic class. And this mapping enables easy integration of CAN devices, ECU sensors, actuators in TSN networks, but also it allows monitoring, control, diagnostic of multiple CAN networks over a single TSN node. And then what the whole gateway is based on CAN frame tunneling over UDP, which comes at a steep cost of bandwidth waste, if you may, because of the whole overhead of headers. And what we did on that end is that we proposed a method that allows you to trade latency with for better bandwidth utilization. Thank you all.